All right, so good morning. Hello, good morning. Yeah, hope you're having fun so far. We had a breakfast. Hope you had a chance to do breakfast. And there were some changes in the email I communicated already. So this is day 2. We will have another distinguished speaker today, David Gesbert from EURECOM, where he is a director and a dean. And David got his PhD in Telecom Paris in 1997. He was with Stanford, and also he was doing some startup jobs over there, I guess, which become company now Intel, right? And he was also, before joining EURECOM in 2004, he was also with part of University of Oslo. David has a lot of articles, like 350 articles, 25 patents, and recipient of 5 best paper awards. Very impressive. And he has also awards like chair in the area of AI for future IoT, as well as Grand Prix in research, jointly from IMT and the French Academy of Sciences. So with that, I would like to welcome Professor David Gesbert for his talk. Please join me in welcoming him. Oh, sorry, we missed it.
Thank you. Thank you, everyone, for having me here. Is the microphone working? Good? Okay. Let me set the clock. Yeah, thanks very much. So I've been doing research, but my research community has been so far rather in the communication society, information theory society, and the signal processing society. So this is the first time, actually, I attend a conference from the computer society, and I find it really, really interesting to see if we can interact and if they have overlapping interest. I'm pretty sure they are. The talk I'm giving today actually would not be something typical of, I would say, for example, in information theory society, because I have a lot of experiments which we are building on campus for what we are going to talk about today, which are flying robots mixed together with wireless networks. And I hope that there will be interest here in this community in the things that we do. So I will be talking a bit about learning. So there's been, when I say learning, I mean trying to estimate a number of things and a number of parameters. I will describe later. I will be talking about sensing. Sensing has become a key topic in the context of next generation wireless networks. I'm not sure if you are following the progress of standards on the road to 6G, but sensing is one of the KPIs that people are trying to address. And by sensing, we mean different things. We mean maybe localizing nodes, localizing phones, localizing anything that is connected to the network, and also mapping, trying to recognize the environment and use RF signals in order to map the environment and recognize objects in the environment. Okay, so this is what sensing is about. And I will be talking about that, but I will be talking about that in the context of flying robots. So basically micro-scale UAVs, which are thrown into a wireless network for specific purposes. I have to say that there's a lot of talk about the convergence between robotics and wireless networks these days. But for the most part, what people are worried about is mostly how to address robots as clients in a wireless network. So basically replacing people with phones with robots that need to be connected in order to perform the task that they are supposed to perform in factories and in cities and elsewhere. Here, my point of view will be a little bit different. The robots I will be talking about, they are not clients. They are not trying to access the network or to get data from the network. It's the opposite. The robots are thrown in by the network service provider in order to help improve the performance of those networks. Okay. Typically for sensing capabilities. So this is the context. Before I do that, let me just one slide to explain where I'm coming from. Actually, I'm French. So I'm rather local, although my lab is located in Sophia, Antipolis, which is 1,000 kilometers away from here, so it's not that close. We are located in a high technology park called Sophia Antipolis. It's one of the biggest in Europe. So there are many labs from companies and universities. And there is my lab is there. EURECOM is actually both a research laboratory and a graduate school. And what is interesting about it is that it's actually an academic joint venture. It's a joint venture between a number of good top-level universities in Europe, joining forces and sending students on a common campus in France. And we also have a number of companies on the board as well. Feel free to come and visit if you're interested. Okay, coming back to my talk. So, what is the basic idea? The basic idea here is to say, I have a wireless network. I want to improve performance of this wireless network. And I want to see if there's a use for robots as part of the infrastructure. Okay. So what is interesting with a flying robot, with a UAV, is that there is a 3D capability, so it can move around. And essentially, it means that you will be able to position this piece of infrastructure at the right place, at the right moment. And if you program the robot with enough intelligence, you can make it sufficiently autonomous, such that by itself, it will recognize where it has to go at what time in order to help the network the most. So that's the objective we have in mind. So why would you want to do that? So there are a number of use cases that we have been looking at. And we've been looking at both at the theory level, algorithm design, and also trying to come up with experiments and hardware. I will show you pictures later in the video. So I've considered today 3 use cases. The first one is called energy efficient IoT data harvesting. In this setup, you basically have an IoT network. So you have an Internet of Things network. You have a bunch of sensors that have been scattered around, maybe in an agricultural setting, or maybe in a large factory setting. And those sensors are actually collecting data locally. And the idea is for the network to suck up all this data and analyze it. So you could, of course, ask the sensors to communicate this data over the air by connecting to a local infrastructure, maybe some fixed network. And this is what is done today. Or you could perhaps inject a flying piece of network that's going to move around and that over time is going to collect the data from the sensors by flying as close as possible to those sensors and in a minimum amount of time. Why is that interesting to do that? Well, you know, in wireless networks, the closer you get between the transmitter and receiver, the less energy you need to use in order to communicate a given amount of data. So you can save a large amount of power by bringing the infrastructure as close as possible to those IoT nodes, which is something you cannot do with a fixed network, but now you can do if you have a flying robot that actually carries a base station. So we'll see how we can explore this. The second one is robot edit sensing and localization. That's another setting. That's a setting where I have a bunch of radio nodes that are scattered. Typically, could be people, for example. They are lost. I want to localize them as closely as possible. Okay. So localization is one of the KPIs in wireless networking. This is something that is typically done by using measurements collected by the local infrastructure, by base stations. And if you have enough base stations, enough antennas in the infrastructure, you can collect enough data, and by triangulation, you can localize your your radio nodes. The issue is that when you have a complex propagation environment, like a suburban or city environment with no line of sight and path reflections and blockage, the accuracy you get by triangulation is quite poor. GPS is helpful, but GPS itself is also not extremely accurate when you have a complicated propagation environment. So there the idea is to say, okay, I inject a robot that is working for the network, and the job of that robot is actually to collect data in order to localize the ground nodes as accurately as possible. The third one is called autonomous relays for coverage extension. The setting there is that you have a network that's been deployed, but you have people that are on the edge of the network and don't get good coverage. So you could install new infrastructure, new base stations, but that is very expensive, especially if this is for a temporary use. Maybe there's a concert, maybe there's a sport event with a massive amount of people going at a certain place for a temporary amount of time. And you would like to provide service only at that moment, at that space. There, maybe you can imagine throwing a flying robot that acts as a flying base station that will move there by itself and provide internet access to those people. That's coverage extension. All right, so the first one is just covering theory, and the other ones I will show you videos to show experiments we have built on campus to realize those objectives. Okay, the first one. So the first one, because it's theory, it has a few equations, but it's not, I don't think it's that complicated. I will try to extract the main meaning of the models that we're using today. So power efficient IoT data harvesting. Again, I have, let's see if this works. Do I have a pointer on this? I don't see anything. Okay, it's okay. No worry. So I have a number of IoT sensors that have been scattered around. I don't know where they are, okay? They are random locations. Except I will assume I have a few what I call anchor nodes. So these are a couple of those sensors. I actually insert them at the place that I know in advance. Okay, you will see why this is useful. But for most of them, I don't know where they are. They are collecting data, and I have a number, not just one, but multiple robots that they're going to fly in the air. And those robots, their job is to coordinate with each other and fly at the places where they'll be able to collect as much data from those IoT nodes as quickly as possible. So I give them a flying energy budget, which translates into a flying time, maybe let's say 1 minute, 2 minutes. I also provide, as a prior information, I provide a 3D map of the environment to the robots. So they know where the buildings are located, but they don't know where the IoT devices are located. So everything else, like I said, is unknown. So I don't know where the ground nodes are located. I don't know how propagation behaves. Propagation is a very complicated matter. Of course, can be modeled by simplified models, sometimes oversimplified. Here, I don't know. It depends on the structure of buildings, how many buildings, where they are. So I don't have in advance a model that I can use. And to make things even more complicated, I'm going to ask those robots to self-optimize their trajectories so that they efficiently collect the data as quickly as possible. Because I could also have designed random trajectories and collect the data along the way. You could collect probably some data doing that, but it won't be efficient. So I really want to optimize the flight and the trajectory of those robots. Okay, so this can be translated into an optimization problem. And let me comment on this briefly. So this is what is in the upper left corner here. I want to maximize a total amount of data. Let's see if I can move. Total amount of data, which is this notation C here. The amount of data I get depends on the location of the IoT nodes, which is letter U, the location of the robots, which is the letter V. M is the index of the mth robot. N is the time index. Okay. So I have a capital N units of time. I have K nodes on the ground, and I have capital M robots. And I want to maximize the data that those robots is collecting over M times. And I want to do that within a limit of capital B energy being spent. Okay. I also specify the starting place and the finishing place of those robots. Now, the data function is represented using a simplified Shannon type model. So the data you get at any point of time, it will depend on the logarithm of the signal to noise ratio between the IoT node and the robot. Okay. And which itself will depend on the distance. So you're further away, then you collect less data. If you're closer by, you collect more data. But it also depends on whether there's obstacles along the way between the robot and the IoT node. So it depends whether you are in line of sight or non-line of sight environment. But this is something you don't know in advance because you don't know where the IoT nodes are located. So you have to imagine that for the robot, this is sort of an impossible task because they fly up in the air and they are supposed to go and visit IoT nodes that they don't know where they're located. So how do you do that? Well, what you do is that you break down this problem into a series of separate sub-problems. The first thing you'll do is that you will try to use what you know in order to first get an estimate of the channel model. Because once you have a channel model parameters, you can use it in order to guess the location of the unknown nodes. So again, you will use, I assume you know the location of a few sensors. I call it the anchor nodes. I will use this information to infer the channel model parameters. And with that, I will be able to guess the location of the other sensors. And once I've done that, I will try to optimize the trajectory of the robots. Of course, in practice, I will do this in parallel, not in sequence, but in order to explain, it's better to explain sequentially. Okay. So this gray box is kind of a big model that each of the robot is going to try to optimize or estimate. Okay. In this model, there is the channel model parameters. Okay. And the second part of the unknown things are the location of the IoT nodes. So again, you use the location of a few anchor nodes as a way to, by measure, first of all, you measure the RF signal power at the robot coming from IoT nodes at known location. With that, you can infer the channel model parameters. And once you have this information about channel model parameters, you can start guessing the location of the other IoT nodes. How do you guess the location of the other IoT nodes? Well, you have to resort to non-convex optimization algorithms. And the one we try here is particle swarm optimization, which means that you start off with a number of wild guesses for where those IoT nodes might be located. And then you refine step by step by only keeping the guesses that seem to be matching your measured signal power levels. So you iterate back and forth, and with that, you'll be able to guess the location of the IoT nodes. Now, how do you optimize the flight of the robots? remember, you want them to move in a way that's coordinated. What you don't want is that you don't want to have the robots go and get closer to the same IoT nodes, because that would be redundant. It would be better if you have, let's say, two robots that they partition the space and they sort of agree that one robot will visit the east side and the other robot will visit the west side, so that as quickly as possible, they collect together all the data. So how do you get this behavior, this cooperative behavior among agents that in principle, are not fully coordinated? They don't directly communicate. So there are a number of ways you can explore, but because here the amount of unknown quantities in the beginning is so high, we resorted to a learning method that is suitable for this kind of case, and these are the methods based on reinforcement learning. So in reinforcement learning, you have an agent that in the beginning doesn't have much knowledge, and that is there is a learning from trial and error. Is learning by taking actions and observing the rewards it is getting for each action and collecting a memory of those rewards, and based on that is able to improve step by step the future actions. So that's roughly the principle of reinforcement learning. The problem with reinforcement learning is that this is a very slow process towards convergence. So if you were trying this in a real robot and hoping to get the optimal behavior, the optimal trajectory, you will need to fly many times this robot before you actually converge towards a good trajectory. But when you're dealing with real robots, you don't have that luxury, and you have to find a method that allows you to converge as quickly as possible. So what we did is that we modified the reinforcement learning approach. So first of all, this is multi-agent because you have multiple robots. So there are already a number of algorithms that exist to train multiple agent another reinforcement learning framework. But what we've done is that we went a step further by inserting a model in each of the agents. So the model I was explaining here, this is where it's going to be implemented in each one of the robots. So we call it model-aided reinforcement learning. That's one step. The second step is that you don't want each of the robot to come up with their own model independently. You want them to help each other by making sure the models are consistent with each other. So for that, we will use some form of aggregation. So this is very similar to what has been proposed under the concept of federated learning, except here it's federated learning across these flying robots. So again, each robot will have a model which has been presented before, and then iteratively I ask each robot to send the weights to an aggregator that's located on the ground. So this is based in the network, and then the aggregator aggregates and sends back a modified version of the model to each one of the robots, such that the models they use remain consistent with each other. All right, so this is not an experiment, this is a simulation. This is the kind of result you get, for example, using 3 robots having to cover an area. So this area is actually a virtual city. The color you see are buildings, and the different colors represent the heights of buildings. Let me go there, explain a little bit more. Those crosses are the places where the IoT devices are located, which is not known beforehand in the beginning of the learning process. And the triangles are the anchors. So those are IoT nodes with known location. All the robots start off from the same location, and they are being asked to collect as much data as possible from the IoT nodes. And what you see here are the trajectories followed by the robots. But this is, of course, after convergence. I will show you later the amount of time it takes to converge towards this behavior. But once you get it, it's quite nice. You see how they divide and conquer. They divide and go and visit the neighborhood of a different subset of the IoT nodes. So that when the energy budget has been consumed, they have collected maximum amount of data from those IoT nodes. So this is a curve showing the learning process across time or across the number of learning episodes. And the y-axis tells you how efficient data collection has been. So this is a number between 0 and 1. 1 would be that you've managed to collect all the data that has been buffered in the IoT nodes. And 0.5 would mean that you collected only 50% of the data. Okay. So a better result would be a curve that would be above the other one. So for example, here, the red curve is the better one, and the orange curve is the worst one. So we compare different approaches. We compare, first of all, we started off with a classical implementation of reinforcement learning, okay, which is, in this case, Q-learning. And I means independent. So independent Q-learning, it means that those robots are not aware of each other. They are trying to learn their optimal trajectory, unaware that there's another robot in the neighborhood that is trying to accomplish a similar mission. Okay. Then the next one is by having a multi-agent version of reinforcement learning, where this time the robots are aware of each other's presence, and over time they are actually having some form of cooperation. So this is the green curve, which allows you to learn faster. And then the blue one is what happens where you start injecting a model in each one of the agents. So this is a sort of a departure from the classical reinforcement learning, where normally there's no model there. But if you insert a model, because after all, we are networking and wireless experts, so we have a basic understanding of how nature works. We have understanding of channel modeling, and why not use that and inject that into the robot, and then you get the blue curve. And then the red curve is what happens when you force consistency across the models by having this federated framework. So by aggregating the models into the network and making sure that all the robots have consistent models. Okay, so you see the gain in learning speed is significant. So this is just algorithm theory. Now let's move to something a little bit more challenging, which is trying to implement something in practice. So let me tell you first about the use case for which we did this, which is robot-aided sensing localization. So this is about trying to localize some lost devices. Those devices, of course, are connected to the network. They are emitting some signals in order to try to be recognized by the networks. And the robot is going to listen to those signals and use that in order to pinpoint the accurate location of the node. Okay. So localization is a big topic in wireless networking. It has been a big topic in 5G. It's becoming an even bigger topic in 6G. The classical approach, as I mentioned before, is triangulation. Triangulation means that you collect typically time of arrival data between fixed base stations and the IoT or the radio node that you want to localize. And by if you're assuming that you are in line of sight environment, you can triangulate by simply looking at the intersection between the circles that represent the radius of propagation corresponding to this time of flight that you have measured. This is an approach that works really well if you have a clean line of sight environment. As soon as you have a non-line of sight environment, this approach does not work very well. Because what happens is that when you measure a time of flight between your transmitter and the receiver, for example, here, you may measure something that seems to be coming from an object that's further away. But that's just because the path has reflected onto some objects. And therefore, it's very difficult to localize accurately when you have reflections on buildings. So how do you solve this problem? Well, the idea here is to why not inject a robot that's going to collect data and help the network improve the localization accuracy by coming up with this additional data. So why is it that a robot would do better than a fixed base station? Well, precisely because the robot can move at location where the data you measure is in fact more meaningful than what can be measured by a fixed base station. For example, a robot can move around and at some points will be in non-line of sight from the user you train localize, and other places will be in line of sight. So you can collect richer data, and overall you hope to improve the localization accuracy. So that's the basic idea. So in this picture, I show you the basic framework. What you see here, the stars are the location of the flying robot. Initially, we assume that the robot describes a random trajectory. Okay, not trying to optimize that. Maybe a straight line, maybe a circle, doesn't matter. You here is the user we're trying to localize. Whether you have one user or multiple users to localize, it doesn't matter because you can run these algorithms in parallel and localize multiple users at the same time. So let's just focus on localizing one user, which is here. So I don't know where this guy is located. I might have a fixed piece of infrastructure. So this is a base station, a classical base station. Okay. All right, so now I have different kinds of measurements. All the measurements are of the nature of time of arrival. This is what is typically used in localization. This is critical. It tells you the duration that has elapsed between the moment a pulse was emitted and when it was received. And again, you can try to translate that into a path length. And this will be efficient if you are in line of sight, but this will not be efficient if you are in non-line of sight. Nevertheless, you have the robot flying around, and at each location of the robot, you're going to collect these T are measurements of time of arrival. So you will collect here, collect there, collect there. At the same time, the base station is also collecting time of arrival data. You can also collect time of arrival data from the user, but also from the robot. Why do you do that? Because you will see that we use a GPS on board the robot to try to have a rough idea of where it's located. But the GPS accuracy is never good enough. We are trying to shoot here at accuracy of 1 or 2 meters for localization, and GPS is not going to give you that. First of all, and also the robot itself is vibrating, is moving around, there's a fair amount of noise in the location of the robot itself. All right, so now what is the framework? Well, over a certain trajectory, you're going to collect all these time of arrival data. And then you're going to form a system of equation to try to match those measurements, time of arrival, with the unknowns. The unknowns are the location of the user. And I'm going to throw in also the location of the robot, because I said you have an estimate of it, but it may not be accurate enough. So you also want to refine that. Right. You also need to classify those measurements because you will treat line of sight and non-line of sight in different ways. So how can you classify non-line of sight versus line of sight measurements? Typically by the amount of noise you get in the measurements. But in the beginning, you don't really know. Now, the algorithm you use to match the time of arrival measurements with the location estimates essentially becomes a least squares approach, a least squares optimization program. So you can solve that. Now the question we are throwing it is, where is it that the robot should go? Are there locations where the robot should go that make localization more accurate? Okay. So this is actually a quite challenging problem. Remember that the robot is not aware at the beginning of where the users are located. So asking the robot to optimize the trajectory in order to improve the accuracy of localization is something that's quite challenging. So how can you do this? You need a metric. The metric, there are different kinds of metric you can use, but it has to be a metric that reflects the accuracy with which localization can be carried out. So there is, in estimation theory, there is a metric called Fisher information that has been used historically to measure how much, if you have access to a certain amount of measurements, those measurements depend on an unknown parameter. You can model the optimum accuracy with which you can estimate the missing parameters based on those measurements. And it's regardless of any algorithm. So this Fisher information matrix, which is noted by F here, is something you can estimate. And then what we ask the robot is to move step by step, to move at location where the Fisher information will be reinforced, will be improved. Okay. So this is a step-by-step algorithm. This is a greedy algorithm. I'm not trying to optimize the entire trajectory at once, because that would be something that is too expensive from a computation point of view. But if you do it step by step, you can actually do it. This has some relation with what people call active learning in robotics, which in principle is a slightly different idea. In active learning, you want to, so it's a learning framework where you have access to data, but you know in advance that some of the data are more meaningful than others, and you would like to just discard the less meaningful data and only keep the most meaningful data to have a more efficient learning process. That's exactly what you do here. By moving the robot at particular location, you are making the robot accessing the more meaningful data, and you are avoiding to waste your time at location where the data would not be so meaningful. Okay. And this is the sense of this optimization algorithm here. Okay. So first, before I show you the proof of concept we built, this is a simulation of this algorithm. So the video started, it's a little bit fast, but basically this is, this is again a virtual city. The robot started at the one given location. You give a flying time budget. Then you have a number of, so in this case, you want to localize those users here. These are the fixed base station that you use to triangulate. And the robot is flying around and collecting time of arrival data. And you, together with the fixed base station, you localize the thing. So you see that actually now your estimation has been good because the estimate and the true locations are at the same spot. But let me show again the video so you can see the stars moving around. and converging towards the true user location. All right. So this is just one snapshot of a simulation. This is maybe more meaningful. This is a Monte Carlo experiment to show the advantage of using a robot for localization compared to just using fixed infrastructure. So this is a CDF curve. The x-axis is the localization accuracy or error between 0 and 50 meters. And then you have the CDF curve for this error. So you want to have a curve that's on the left side as much as possible. Now, the black curve is what you get by trying to localize with only fixed infrastructure. So here in this case, 5 base stations. So the median accuracy, as you can see, is around 20-something meters. The red curve is what you obtain by replacing one of these base stations by one movable base station, this flying robot. So one UAV with 4 base stations. But in the red curve case, I'm not trying to optimize the trajectory of the robot. It's flying at an arbitrary random trajectory and collecting data along the way. And actually, you can already localize with that. It's just, it won't be as efficient as you can. And the blue curve is what you obtain by active learning and by having the robot fly to locations where the time of arrival measurements are as meaningful as possible from a Fisher information point of view. So you see the gains that you obtain. All right, so this is the theory, but we actually try to build something here. So the picture you see here already show you the type of object we build in the lab. So these are quadcopters that are roughly this size. There's no product you can buy off the shelf that will do all the things you want the robot to do. So you have to assemble most of it yourself, including all the frame and hardware is fully customized. The point when I show this picture, I want to show you is that there's a lot of issues that people don't think about, at least we didn't think about in the beginning before attempting this experiment. A lot of problems that that occur. For example, this thing here is full of radio equipment. There's GPS, there's a remote controller for safety backup, because in the end the robot is autonomous, but you want to have a pilot to avoid potential crashes, which do happen. And then you have the communication between the robot to the UEs and to the infrastructure. So you need a 5G setup for that. So you need a 5G transmitter and receiver. So a lot of interference issues, a lot of coupling issues between antennas that you need to work out. So the positioning of the antenna is actually pretty challenging. Power amplification also was a big problem. Very, very hard to come up with a power amplifier off the shelf that is compact enough to be mounted on these robots. So we had to design ourselves. Energy autonomy is a huge issue. These things are flying 20-minute stops. So, for an experiment is okay, but you wonder how you will deploy that in a real service. But we do have ideas on that if you want to discuss that later. And the last one is all the 5G communication protocol implementation. How do you do this? Do you buy an off-the-shelf Ericsson, Huawei, or Nokia equipment? No, you don't, because remember that you need to be able to play around with the protocol, go and access the measurements you want, all this time of arrival data, and analyze that for localization. You just cannot use ready off-the-shelf commercial equipment. So you need to deploy something that is completely, I would say, open source, accessible, non-proprietary. Okay, so for that, we use something called open air interface, and I want to have a quick focus on that, because it has really a lot of potential I mean, for our experiment, but I believe also in when you try in your own labs to experiment with 5G or 6G setups. Let me make a quick survey here. Who in the room has heard about open air interface before? I assume not many, because this is not communication society, but still. Okay, like 5, 6 people, so a small minority. So open air interface is what is that? It's an open source implementation of the 3GPP standard. Okay, and it's evolving with the standard. So today it's a 5G, and tomorrow there will be a 6G version of open air interface. This was created in my lab 10 years ago for just internal experimentation purposes. But because it was open source, we decided to make it accessible to everybody else. And we turned it into a software alliance where companies and academic labs could join, get the source code, and experiment with wireless protocols in their own institutions. And I have to say, this has been now a resounding success. We celebrated the 10-year anniversary, in fact, 3 weeks ago on our campus. And you see all these companies. So we had people from all these companies coming over, because these are companies now that are the big donors. They are actually funding this software alliance. Not so much to make their products, but because for experimental point of view, an open source architecture and software is so useful that it is of interest, not just to academia, but also to industry. So if you have questions about this, let me know. Any one of you can easily become a member of the alliance. And if you are from an academic lab, it's free. You just get the code and start tomorrow experimenting. So first, it was extremely useful because we could access a full stack implementation of 5G and deploy it on our robot. Okay, so this is how it looks like. This is the robot I showed you before. The robot is going to communicate both with a UE. Remember, this is the UE I'm trying to localize. I don't know where it is, but this UE is actually communicating, okay, some control signals. The robot is also communicating to the infrastructure. So on our campus, we have a fixed sort of base station antenna. And this base station antenna is connected to the network. Okay. We also deployed or developed a software for visualizing what's going on in the robot and being able to control operations. And this is something called Q ground control. Sorry. You will see exactly what it does. Okay, so this is a picture of the campus. So again, the setup is like this. There's a mobile phone. There's an off-the-shelf mobile phone that we put somewhere in the forest here. It's at unknown location. There is a fixed antenna that represents the network provider. So it's a base station. And then the robot is going to fly and try to identify the location of the unknown UE. All right. So this is actually a picture, a video we released a couple of weeks ago now. It's very recent. That shows the result of this experiment. Okay, so this one I've already explained. So again, the robot is collecting time of arrival data from the UE at different location, and is using that to triangulate in real time. Right. Okay. This is what you can visualize using this Q ground control software. So this is the real life situation, and this is the virtualized situation happening at the same time. Okay. The red spot is the next location for the robot. Remember, the robot is always trying to find the next step that will enable accurate localization. It's a step-by-step process. And the blue spot is the estimate of the UE location. So you want the blue spot to be close enough to the green spot. So by the way, this is an experiment at 40 megahertz bandwidth. So whatever you do, you'll be limited by the accuracy you can get with a 40 megahertz bandwidth, which is going to be a couple of meters, 2 to 3 meters. Okay. So you see now what happened. Too late, but the blue spot was not exactly on top of the green spot, but it was about 2 to 3 meters away from it. All right. Yeah, I'm going to wrap up very quickly, because the last one was just to show another experiment using the same principle, the same hardware, same robot, same open source 5G, but this time for coverage expansion. All right. So in this setup, it will take a minute. I don't want to localize anything. I want to provide coverage to a node that is out of coverage. So the out of coverage terminal, in this case, to make it more fun, is going to be another UAV. You have a UAV that wants to access the internet. Somehow the propagation is too far or blocked towards the base station, and you will use another UAV that's going to come in as a relay. Okay, and what you will see is that this relay will try to optimize its location such that you maximize the flow, the throughput between the end-to-end throughput between the network and the final terminal. Works. Yeah. So this is actually the relay terminal, and now you will see the relay robot, and the terminal, the final client is the one now. So what we do is that we're going to move around this guy here over space and see how the relay reacts. Remember that the relay is an autonomous robot that is trying to find the best position it should go to serve as the most effective relay. So there is a min-max optimization going on, because you want the link between the base station and the relay to be high, but also between the relay to the terminal. Okay. I guess you saw the video. All right. That's it. So thank you very much. You saw the 3 use cases I wanted to show you, and maybe some of the challenges we are dealing with to experiment with those tools.
All right, thank you.
Any questions?
Question time now. Okay, like he lifted them. Oops.
Thank you for your talk. I have a couple of questions, one more about societal impacts of what you talked about, and another technical question. When you were explaining the scenario, I can't help but envision a New York Times article saying government is flying drones to track people. So can you talk a little bit about the public perception of sensing applications that is coming up with 6G, tracking people with UAVs flying around?
Mm-hmm.
And the second question is, what do you think the impacts of low orbit satellites like Starlink will help with this application, whether it will have any implications on that?
Yeah, for the public perception, I'm aware of the issue. By the way, forget about robots. 6G alone is a huge challenge for public acceptance. And we all have to realize here that this is going to be an issue. It has been an issue with 5G. In France, people have been burning down base station towers, yeah, because they thought that this propagates viruses. I mean, so who knows what the conspiracy theories will be about for 6G, but there will be, it should just be worse. Well, the reality, let's not confuse the perception with the reality. The reality is that the network already can use RF measurements to localize people. Not people, not physical bodies, people with phones, right? We're talking about people with phones. So this is already happening. So the robot is here just to make sure that we have a more accurate positioning of where you are. But we're not, I'm not assuming that people are revealing additional data compared to what they already revealed to the network. Nevertheless, you're right that when people will see UAVs flying overhead, that's going to be an issue. And this is, I think, one of the reasons why today the regulatory is very strict. These things you see here, can fly on campus, but that's it. I'm not allowed to fly outside of campus and not above any kind of inhabited areas. So I have to deal with that. I fully understand it. But my guess is that things will change. A few years ago, nobody would imagine that having driverless cars in the streets would be allowed anywhere. And now there are cities where it's allowed. Okay, in San Francisco and a few other cities, you see driverless cars. So things are going to evolve and people will start to slowly accept it. And my guess is that it will just be the same with UAVs.
Second question, I guess, right? Thank you.
We can talk about the satellite later.
Oh,
Yes, excellent talk. In the CS community, especially mobile computing community, there was some work on delay tolerant network, which used the no movement for package delivery, store, carry, and and movement. Also, there's another community, like many AI studied swarm intelligence, which is a collective behavior of self-organized, decentralized system. So can you comment on the relationship in your community and CS or network community?
Well, only to a limited extent, because as I said, I am not extremely familiar with computer networking community, okay? But I'm aware of the delay tolerant studies that were being done. But we're talking about different kinds of delays. If you are waiting, I mean, are you referring to the IoT data collection process, maybe for your first question? Let me go back to this one. Here, the goal, I mean, you tell me if it's related, but here the robots are collecting data from the IoT devices, but they are not carrying the data anywhere. I only want to collect the data at the drone itself for analysis. So it's not so much an issue of I mean, it's not the same setting where you have a network where you have a lot of different devices trying to communicate to each other. Here, it's really more like fusing data, collecting data all at a single point. So I'm not very sure that this is the same framework we're talking about here. Yeah.
All right. Oh, there are so many questions, so yeah, I can be quick.
I want to ask about the efficient IoT data harvesting. So how the ground nodes are aware of the UAV nodes, then they start transmitting?
Oh, they are not. We're assuming that those nodes are transmitting. They are, they know that they connect to the network. They just don't know that it's a robot. So whether for them it's transparent whether they communicate to a base station or to a flying robot. Okay. So this is the question that they don't know.
Thank you very much for your talk. How do you see this scaling in terms of use cases? What's the ideal scenario for you? Like robots extending coverage for users in a city? Would we have skies full of UAVs? How does this scale? And the second question, I don't know if you mentioned, do you use O-RAN in this or?
Not in my experiment. So So O-RAN collects a number of specifications for open access networks, and there is a collaboration with Open Interface. But in my experiment, I only worry about the lower layer communication on campus. So I don't have to deal with O-RAN. How does this scale? I don't know. We will see. I mean, right now, this is a small scale set of experiments. If you ask me, the coverage extension is not going to be used widely, but for example, for certain type of events, like I said, sport events or social gatherings, where you need extra coverage. It's not so much that you don't have any coverage at all, but areas where you have a limited coverage and you want to provide additional capacity a certain amount of for a certain amount of time, then I think it does make sense. Otherwise, if you don't do that, you have to come in with trucks and bring antennas on trucks. And I'm guessing that actually using UAVs is more cost efficient.
Okay, tomorrow one, if you have questions.
Thanks for your presentation. I'm not from your communications community, so I have two questions about the quality of the results. Like in the data harvesting case, you presented results where you didn't even collect 90% of the data. It was like 85%. So question is, how good is this? And then also with regard to the localization results, you mentioned it's like an error of 2 to 3 meters. Isn't GPS better?
Oh, okay. No, because in non-site environment, GPS is actually very random. So what we observe is you have accuracies of more like 10, 20 meters.
Okay, I doubt that this is in the environment that you had in the demo. And can you comment on the quality of the data harvesting results?
That's just, it depends on the parameters of your experiment, and it depends on your flying budget. So of course, if your flying budget is extended, you can collect up to 100% of the data. It's just that for this particular experiment, the flying budget was such that I was not able to collect the data.
Okay, just one last question. I know I promised, or maybe two more. Okay, Dario. Oops.
So thanks. One curiosity, in the demo you were showing the UAV were flying, have a think time, and then move around. I wanted to know if this think time, what is the component that is due to sensing and what is the component that is due to computation? You were also mentioning, decision to do onboard versus offloading. So if you can comment on that.
Yeah, I don't think it's so much thinking time as much as, sorry, the manual operator launching the system and, sorry, and starting this Q ground control environment. So there's a bit of manual operations there that takes a few seconds. It's not so much the computation time.
Yeah. So the sensing, you don't need to collect a lot of sensing. It's not like you need to collect 10 seconds of worth of sensing. Is more, what is the time scale of the sensing you?
Thank you. Not sure what do you mean, the time scale of the sensing?
For instance, in the localization one, you see the drone moving, then stopping, and then moving again. So there is supposedly running autonomously to the next direction to maximize efficient information. So my question is, how much data you need to sense for how long before being able to take the next greedy step?
I don't know. I guess it depends on the power you have on board, because the computer we have on board is a really small scale. We use these aboard mini computers, and because of the weight limits, there's only so much capability you have on board. So I wouldn't be able to answer that question.
I have one last over here. Yeah, thank you. This is the last question.
Thank you very much for the great talk. I would like to hear about your experience on open air interface project that you mentioned. I understand that it's a lot of effort in terms of development, and typically researchers are not expected or do not have resources or time to do a lot of development. So I want to hear how you funded that effort, how you sustained it, how you managed it. Thank you.
Okay, well, it can be a long question to answer.
Very quickly, one.
So very quick, huh? But basically, there are two components in this OAI framework. First, you have the community. So people like you, for example, might be interested to use and maybe contribute. And then we have also a team of people on campus, which is funded by the donation of those companies. We have a team of about 15 engineers. Those guys are working full-time now to maintain the code. So the bulk of the effort to maintain the code, upgrade the code with the evolving standards is basically a team of 15 people. And then you have all the ecosystem with people in companies and labs contributing once in a while. It's hard to measure exactly what is the power of those people, but it's also quite significant.
All right. So thank you for the speaker once again.
Thank you so much. Thank you.
Yeah, as a token of our appreciation, we would like to also give you some small gift as well as a
Oh,
certificate.
the best paper award.
It's something like that.
Okay, thank you.
And
Thank you so much.
the other thing is actually like for next year, thanks to our steering committee, if you submit a paper as an author, that will be free registration
Oh, so
for
for
you.
me.
Yeah, for
fantastic.
you, you should be author for that.
What about the flight ticket to Sydney?
It's very close.
Ah.
All right, just
Thank you. Thank you.
what mean.
Thanks so much.
Thank you. Yeah. So that concludes the session. We'll have a coffee break and we'll start at 10:30, please.